Hello and welcome. In this video, I'm going to talk about aspects of solubility. We've got gases, liquids, and solids that can all three possibly dissolve in water if there are appropriate intermolecular forces. This will be key to understanding the solubility lab, lab 2 in my class. So let's get started on this. So first of all, let's discuss some definitions of solubility. So a solution is a homogeneous mixture, okay? It's solute and solvent, all right? The solvent is the substance in greater amount, that's usually liquid water. And the solute is the substance in lesser amount, and this can be a solid or a liquid or a gas that's dissolved into that water. But again, a solution can be anything. The air in this room is a solution of different gases. If you look at jewelry, for example, it's going to be a solution of gold, possibly copper, zinc, some other metals. It depends on what kind of gold it is. Now, when we're talking about solubility, we are talking about the maximum amount of substance that can dissolve per amount of solvent. Okay, so sodium chloride, for example, is going to have a certain solubility. I forget what it is, 35 grams per 100 milliliters or something like that. And if a solution is saturated, it means that the concentration has reached the maximum solubility and no more solid can dissolve in that. Okay, so you have salt water that's as salty as it can be. All right. Now, an unsaturated solution is a solution wherein the concentration is less than the maximum solubility. So, for example, if you want to gargle in the morning with some salt water because you kind of have a sore throat or something, you're just going to put a little bit of salt in that water and stir it to dissolve it. It has not reached the maximum concentration because probably you could add a whole lot more salt and stir to shake it, but then it would be too salty for comfort, okay? In this picture here, we have a saturated sodium chloride solution that's depositing solid sodium chloride crystals as the solution evaporates. All right. Now, we do have a rare situation called supersaturation, and this is when the concentration has exceeded the maximum solubility. And this is for mostly cool demos that you can see on YouTube. I won't talk about that anymore in this class. All right, so we're going to talk about three things: solubility of gases, liquids, and solids, and I'll talk about the rules and features of these. So first of all, think about gas solubility and temperature. We've got methane, oxygen, carbon monoxide, nitrogen, and helium. By now, you're going to recognize these as gases. And you can see we have some curves that go down, okay? So gases can dissolve in water, first of all, okay? That, of course, is how aquatic plants and animals breathe, okay? There's oxygen that can dissolve in water, carbon dioxide that can dissolve in water, and other gases in there is atmosphere that can dissolve in water, okay? Now, gases are less soluble at higher temperature. Very key point. So all of these gases, if you look at the curves that go down to the right. Also, gases are generally more soluble at lower temperatures. Okay, so if we're looking at oxygen, for example, oxygen is going to be more soluble at low temperature. So think about a lake. In the wintertime, is it going to have more or less oxygen than a lake in the summertime? Okay. So you can do this experiment yourself. You can get some cold tap water from your faucet. All right, just pour it into a glass and let it sit on the tabletop for an hour or two until it reaches room temperature. You're going to see as it warms up, there's going to be little bubbles forming on the sides of the glass, and that's basically gases that are coming out of solution. Okay, gases in the Earth's atmosphere include nitrogen, oxygen, carbon dioxide, argon. Okay, when you first boil water, you notice those little bubbles that are on the bottom of the pot or the pan. Those are actually atmospheric gases that are coming out of solution. If you put a thermometer in there, it might read 80 or 90 degrees Celsius, but it hasn't reached the boiling point yet. Okay, then of course, when it's a rolling boil and rumbling and roaring at you, that's when those bubbles are comprised of steam. Okay. The textbook, OpenStax, discusses fish kill. Basically, it's when the temperature of a lake increases quite a bit. This is an event back in July of 2021 in Alberta, Canada. It was 40 degrees Celsius. The actual temperature of the water for some lakes and streams were up to 40 degrees Celsius, and this led to lower oxygen levels in the lakes and streams, and basically the fish drowned. They couldn't breathe. Okay, they died. All right, so let's talk about gas solubility and pressure. We've talked about temperature and how that affects solubility of gases. Now let's think about pressure, okay? Now, we've experienced opening a soda can, probably not this drink here, but gases are more soluble at higher pressure, and that means in the soda can, okay? So there's a whole bunch of gas dissolved in the caramel and the sugar water inside the soda can because it's under high pressure, kind of like think a champagne bottle, okay? But when you open the bottle, okay, or the can of soda and you pour that into your glass, there's all these bubbles of carbon dioxide coming out of solution because gases are less soluble at lower pressure, okay? We're going to skip Henry's law. If you want to know more about that, check out some other videos or the OpenStax chemistry textbook. I don't go into the math in terms of calculating how many grams or what's the pressures and all that, okay? All right, let me talk about liquid solubility. So liquids can dissolve into water. We've talked about ethanol dissolving in water. We've talked about hydrogen peroxide dissolving in water. So these are solutions that you can pick up at the store, and they contain water in solution, okay? So first of all, weird word, it's called miscible. So miscible is when two different liquids mix to form a homogeneous solution. So an example of that would be ethanol and water, okay? So when ethanol and water are mixed, it just forms one homogeneous solution. Immiscible is when two different liquids form to form a heterogeneous mixture. And the most obvious example of this is oil and water. There's two layers, but here on the slide you can see bromine, this very dark brown element in the left test tube, water in the middle test tube, and then you mix these two together, water actually floats on top of bromine because they just don't mix, okay? If you try to stir it up, it just stays that way. It comes back and it separates, much like oil and water, okay? So that's immiscible. Please learn these words for Lab 2, know how to spell them carefully, okay? All right, so let's talk about some examples again for liquid solubility. We're all familiar with rubbing alcohol, I believe. This solution here is a 70% solution. That means that it's aqueous isopropyl alcohol, okay? Now, alcohols exhibit hydrogen bonding if you draw out their Lewis structure, and water exhibits hydrogen bonding if you draw out its Lewis structure. So we have this principle, like dissolves like, and because they're both hydrogen bonding, they can mix thoroughly and they are miscible and form a homogeneous solution, okay? So the like dissolves like principle is kind of like the mantra or the theme for Lab 2. All right, oil and water. So here's olive oil on top floating on some water in a some kind of interesting glass there. Olive oil is hydrophobic. It's mostly hydrocarbons. So if you look at the molecular formula, it's a monster of a creature there. It's C88H164O10. Nobody's ever going to ask you to draw a Lewis structure of this one. But suffice it to say, olive oil does not exhibit hydrogen bonding. Water does exhibit hydrogen bonding, so they are not going to mix, okay? Like dissolves like is not this example, because olive oil is very water-fearing, and water is water, so the two are going to repel one another. All right. Now let's talk about solids and solubility, all right? So we have a graph here from the OpenStax textbook, and you can see how solids are generally more soluble at higher temperature. Doesn't matter if we're talking about sugar, it's going up on the curve on the right. Wow, look at sugar. We can dissolve at room temperature, which is about 20 degrees Celsius, we can dissolve about 200 grams of sugar per 100 grams of water. So there's more sugar than water in sugar water, okay, if we wanted to make a saturated solution, okay? Sugar is extremely soluble, all right? Potassium nitrate, you can see how it curves up. Look at sodium bromide or sodium chloride. The curves are pretty flat, but they slowly increase going up to the right. Yes, there are some exceptions. This cerium-3 sulfate, I believe it is definitely decreasing, but most solids generally more soluble at higher temperature. And the converse of this is true as well. Solids are generally less soluble at lower temperature. So if you wanted to make some nice rock crystal candy, you could make sugar water, heat it up to a high temperature, okay, put in your wooden stick, and then you could slowly let the temperature cool down. As the temperature of that sugar water cools down, sugar is going to be less soluble, so sugar is going to come out of the solution to maintain its saturated concentration, and so you're going to make these nice crystals on the wooden stick. So that's how those rock candy sticks are made. All right. There is an exception, and I like talking about the cool stuff, so here we are, one slide here for my own benefit, I guess, and for yours as well. We have this thing called boiler scale, all right, and it's an exception to the solubility rules. Now, you know tap water contains minerals, and that's why you get the spots on your glasses and other glass dishes when you do dishes and you don't dry off the water, okay? It's precipitating these small amounts of minerals. Some of them include magnesium carbonate, okay? Now, it turns out that at very high temperatures, magnesium carbonate is actually less soluble. And so you build up this mineral deposit on the insides of hot pipes and water heaters and boilers. Here's a cut pipe, and we're just looking down at a segment of it, and you can see how pretty much the whole pipe has been occluded over the years from deposits of different minerals, and that's at high temperature. You might be thinking, well, at high temperature, isn't something going to be more soluble? Won't this be the cleanest pipe in the world? Au contraire, okay? All right, here's a summary slide. Pause the video, write all these down if you want. We've talked about gases, more soluble at high pressure, low temperature. Conversely, they're less soluble at low pressure and high temperature. We've talked about solids, more soluble, higher temperature, less soluble, lower temperature. So that's easy to kind of remember. And like dissolves like principle is a useful kind of mnemonic to help us remember that the hydrogen bonding substances and very polar substances are going to be miscible in water or dissolve in water, and greasy hydrocarbon molecules are not going to dissolve in water, or they are not going to be, they are going to be immiscible in water. Thanks for watching. Please like, please subscribe. I know there was a lot of information, but I hope you got a lot out from this video. Have a good day, everybody.